In the depths of space, where silence reigns absolute and darkness stretches beyond human comprehension, the most violent and spectacular dance in the universe unfolds. Galaxies, those colossal islands of stars, gas, and dark matter, are not the static, peaceful entities they appear to be from our terrestrial perspective. They are cosmic titans locked in an eternal ballet of destruction and creation, a dance so violent and transformative that it reshapes the very fabric of spacetime itself. What you think you know about the universe is wrong. The peaceful night sky, with its gentle twinkling stars, masks a reality of unimaginable violence where entire galaxies, each containing hundreds of billions of stars, collide with forces that dwarf every explosion, every catastrophe, every act of destruction that has ever occurred on Earth. A galaxy collision is not merely an astronomical event. It is the universe's ultimate expression of creative destruction, a process so fundamentally transformative that it challenges our most basic understanding of cosmic evolution. When galaxies collide, they don't simply crash into each other like cosmic bumper cars. Instead, they engage in a gravitational dance that unfolds over hundreds of millions of years, a choreographed catastrophe that tears apart ancient structures while simultaneously birthing new ones. These collisions are the universe's way of recycling matter and energy on the grandest possible scale, transforming the ordered spiral arms of galaxies into chaotic elliptical structures, triggering the birth of billions of new stars, and feeding the supermassive black holes that lurk at galactic centers. To comprehend the true scale of galactic collisions, we must first confront the incomprehensible vastness of the entities involved. Our own Milky Way galaxy spans approximately 100,000 light-years from edge to edge. If you could travel at the speed of light, the fastest possible velocity in the universe, it would take you 100,000 years to cross from one side of our galaxy to the other. But light speed is beyond human experience, so let's use a more familiar reference point. If you could drive a car at highway speed, 60 miles per hour, across the diameter of the Milky Way, the journey would take you over 600 billion years. That's more than 40 times longer than the universe has existed. The Milky Way contains between 200 and 400 billion individual stars, each potentially hosting its own system of planets. If you could count one star every second without stopping, it would take you over 12,000 years just to count the stars in our galaxy alone. Now imagine an object of this incomprehensible size, containing the mass of hundreds of billions of suns, hurtling through space at velocities that make our fastest rockets seem motionless. Galaxies move through the cosmos at speeds that typically range from 100 to 1,000 kilometers per second. Our own galaxy is racing through space at approximately 600 kilometers per second relative to the cosmic microwave background radiation. At this speed, you could circle the Earth's equator in just over 1 minute. But galaxies are not small objects moving quickly, they are the largest gravitationally bound structures in the universe, and when they collide, the energy released is beyond human comprehension. A single galactic collision releases more energy than all the stars in both galaxies will produce over their entire lifetimes combined. The story of how humanity discovered galactic collisions begins with a fundamental shift in our understanding of the cosmos itself. For centuries, astronomers believed that the universe was static and unchanging, a vast collection of fixed stars arranged in eternal patterns. This view began to crumble in the early 20th century when Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory, made observations that would revolutionize our understanding of cosmic structure. Hubble's work in the 1920s revealed that what astronomers had long called spiral nebulae were actually entire galaxies, vast collections of stars lying far beyond the boundaries of our own Milky Way. But Hubble's most shocking discovery came when he measured the velocities of these distant galaxies. Using the Doppler effect, the same phenomenon that causes the pitch of an ambulance siren to change as it passes by, Hubble found that nearly all galaxies were moving away from us. The light from these galaxies was redshifted, stretched to longer wavelengths by their recession. This discovery led to the realization that the universe itself was expanding, carrying galaxies away from each other like raisins in a rising loaf of bread. However, Hubble also discovered something that seemed to contradict this universal expansion. A few nearby galaxies, most notably the Andromeda Galaxy, showed blue-shifted light, indicating that they were actually approaching us rather than receding. This observation provided the first direct evidence that galaxies could indeed collide. The Andromeda Galaxy, located approximately 2.5 million light-years from Earth, is racing toward us at a speed of about 110 kilometers per second. At this rate, it will collide with the Milky Way in approximately 4.5 billion years, creating what astronomers have dubbed Milkometa, a merged galaxy that will fundamentally alter the structure of our local cosmic neighborhood. The discovery of galactic collisions forced astronomers to reconsider their understanding of cosmic evolution. If galaxies could collide and merge, then the universe was far more dynamic and violent than previously imagined. This realization launched decades of observational and theoretical work aimed at understanding the mechanics of galactic interactions. Astronomers began searching the sky for evidence of ongoing collisions, and what they found exceeded their wildest expectations. The Antennae galaxies, located about 45 million light-years from Earth, provided one of the most dramatic examples of galactic collision in progress. These two spiral galaxies began their dance of destruction about 100 million years ago, and the gravitational interaction has pulled streams of stars and gas into long, curved tails that extend for hundreds of thousands of light-years. The collision has triggered intense bursts of star formation, creating brilliant clusters of young, hot stars that shine like cosmic fireworks against the darkness of space. The Hubble Space Telescope has captured images of this collision that reveal the intricate details of gravitational destruction and creation, showing how the ordered spiral structure of both galaxies has been completely disrupted by their mutual gravitational attraction. Another spectacular example is Stephan's Quintet, a visual grouping of 5 galaxies in the constellation Pegasus. 4 of these galaxies are actually interacting with each other in a complex gravitational dance, while the 5th is much closer to us and only appears to be part of the group. The interacting galaxies show clear signs of tidal distortion, with streams of stars and gas being pulled across hundreds of thousands of light-years of space. Radio observations have revealed vast clouds of hydrogen gas that have been stripped from the galaxies during their interactions, creating a cosmic web of material that connects the galactic members. The development of computer simulations in the latter half of the 20th century revolutionized our understanding of galactic collisions. These simulations, running on increasingly powerful supercomputers, allowed astronomers to model the complex gravitational interactions between galaxies over billions of years of cosmic time. The results were both beautiful and terrifying. The simulations showed that galactic collisions are not brief, catastrophic events, but rather extended processes that unfold over hundreds of millions of years. When 2 spiral galaxies of roughly equal mass approach each other, the initial interaction occurs when they are still several 100,000 light-years apart. At these distances, the gravitational influence of each galaxy begins to distort the other's structure. The outer regions of both galaxies are pulled toward their approaching neighbor, creating tidal streams of stars that can extend for millions of light-years. These streams are visible in many interacting galaxy systems and provide a fossil record of the collision process. As the galaxies continue to approach, the gravitational forces become stronger and the distortions more severe. The neat spiral arms that characterize galaxies like our own Milky Way are pulled apart and twisted into chaotic structures. Stars that once followed orderly circular orbits around their galactic centers are flung into elongated, eccentric paths. Some stars are ejected from their parent galaxies entirely, becoming intergalactic wanderers destined to spend eternity in the vast emptiness between galaxy clusters. The first close passage between two colliding galaxies is often the most dramatic phase of the interaction. During this encounter, which may last only a few tens of millions of years, the gravitational forces reach their peak intensity. Vast quantities of interstellar gas, the raw material from which new stars form, are compressed and heated by the collision. This compression triggers massive bursts of star formation, creating stellar nurseries that can produce new stars at rates hundreds of times higher than norm. These starbursts are so intense that they can be seen from billions of light-years away, appearing as brilliant beacons of light in the distant universe. But the story of galactic collisions becomes even more complex when we consider the role of dark matter. This mysterious substance, which makes up approximately 85% of all matter in the universe, cannot be seen directly but reveals its presence through gravitational effects. Each galaxy is embedded within a vast halo of dark matter that extends far beyond the visible stars and gas. When galaxies collide, these dark matter halos interact first, long before the visible components of the galaxies come into contact. Computer simulations have revealed that dark matter halos can pass through each other relatively unaffected during galactic collisions, since dark matter interacts only through gravity and not through electromagnetic forces. This means that the dark matter components of colliding galaxies may separate from their visible counterparts during the interaction, creating complex structures where the dark matter and visible matter are no longer aligned. The bullet cluster, a system of two colliding galaxy clusters, provides dramatic observational evidence for this separation. X-ray observations show the hot gas from both clusters colliding and heating up in the center of the system, while gravitational lensing measurements reveal that the dark matter has passed through largely unaffected. The discovery of gravitational waves has added an entirely new dimension to our understanding of galactic collisions. When galaxies merge, their central supermassive black holes, objects containing millions or billions of times the mass of our Sun, eventually spiral toward each other and merge in a cataclysmic event that releases more energy in gravitational waves than all the stars in the observable universe emit in light. The Laser Interferometer Gravitational Wave Observatory, LIGO, has detected the gravitational waves from merging stellar mass black holes, confirming Einstein's predictions about these ripples in spacetime. Future space-based gravitational wave detectors will be sensitive enough to detect the mergers of supermassive black holes that occur during galactic collisions, providing a new way to study these cosmic catastrophes. The merger of supermassive black holes during galactic collisions represents one of the most violent events possible in the universe. As these gravitational monsters spiral toward each other, they create gravitational waves that carry away orbital energy, causing the black holes to draw closer together at an accelerating rate. In the final moments before merger, the black holes are orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. When they finally merge, the energy released in gravitational waves can be equivalent to the annihilation of several solar masses of matter, all released in a fraction of a second. These black hole mergers have profound implications for the evolution of galaxies. The merged black hole can receive a gravitational wave kick that propels it out of the galactic center at speeds of up to several thousand kilometers per second. If the kick is strong enough, the black hole can be ejected from the galaxy entirely, becoming a wandering supermassive black hole traveling through intergalactic space. Alternatively, the merger can create a single, more massive black hole that continues to grow by accreting matter from its surroundings, potentially becoming one of the supermassive black holes that power quasars, the most luminous objects in the universe. The observational study of galactic collisions has been revolutionized by space-based telescopes that can observe the universe across the entire electromagnetic spectrum. The Hubble Space Telescope has provided exquisite images of colliding galaxies, revealing details of star formation and tidal disruption that are impossible to see from ground-based observatories. The Spitzer Space Telescope, sensitive to infrared radiation, has shown how dust heated by star formation glows in colliding galaxies, while the Chandra X-ray Observatory has revealed the hot gas that is heated to millions of degrees during galactic interactions. The James Webb Space Telescope, launched in 2021, has opened new frontiers in the study of galactic collisions by observing the universe at unprecedented infrared wavelengths and sensitivity. Webb can peer through the dust that obscures much of the star formation in colliding galaxies, revealing the birth of new stars and planetary systems in regions that were previously hidden from view. Early observations from Webb have already shown that galaxy mergers were much more common in the early universe than previously thought, suggesting that most large galaxies, including our own Milky Way, have experienced multiple major mergers throughout their history. The study of galactic collisions has also revealed unexpected connections between these cosmic catastrophes and the formation of life itself. The intense star formation triggered by galaxy mergers creates massive stars that live fast and die young, exploding as supernovae that scatter heavy elements throughout the galaxy. These elements, carbon, oxygen, silicon, iron, and others, are the building blocks of rocky planets and the chemical foundation of life as we know it. Without the element synthesis that occurs in the hearts of massive stars and their explosive deaths, the universe would contain only hydrogen and helium, and planets like Earth could never have formed. Furthermore, the gravitational disruption caused by galactic collisions can scatter stars and planetary systems throughout the merged galaxy, potentially bringing life-bearing worlds into contact with each other. Some scientists have speculated that galactic collisions might facilitate the spread of life between star systems, either through the exchange of material ejected by impacts or through the migration of advanced civilizations seeking to escape the chaos of their merging home galaxies. The future collision between the Milky Way and Andromeda galaxies provides a unique opportunity to study galactic mergers from the inside. Computer simulations of this collision suggest that our solar system will likely survive the merger intact, though it may be flung into the outer regions of the new galaxy or even ejected into intergalactic space. The night sky as seen from Earth will be completely transformed during the collision, with Andromeda growing larger and larger until it fills the entire sky, triggering massive bursts of star formation that will illuminate the heavens with the light of billions of newborn stars. But the Milky Way-Andromeda collision is just the beginning. Our local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, is itself falling toward the much larger Virgo cluster of galaxies. Eventually, our entire local cosmic neighborhood will be incorporated into this vast collection of thousands of galaxies, participating in an even grander dance of gravitational interactions and mergers. The study of galaxy clusters has revealed that galactic collisions are not isolated events but part of a larger process of cosmic evolution driven by the gravitational collapse of dark matter. The largest structures in the universe, galaxy clusters and superclusters, are still growing through the accretion of smaller groups and individual galaxies. These ongoing mergers heat the gas between galaxies to temperatures of tens of millions of degrees, creating vast reservoirs of hot plasma that emit X-rays and can be observed by space-based telescopes. One of the most puzzling aspects of galactic collisions is their role in the formation of elliptical galaxies. Observations show that most elliptical galaxies are found in dense environments like galaxy clusters, where collisions and mergers are common. Computer simulations confirm that the merger of two spiral galaxies typically produces an elliptical galaxy, suggesting that these smooth, featureless systems are the end products of galactic violence. However, recent observations have revealed that some elliptical galaxies contain complex internal structures, including shells, ripples, and embedded disks, indicating that their formation history may be more complicated than simple merger scenarios suggest. The discovery of ultra-diffuse galaxies, objects with the mass of typical galaxies but spread out over much larger volumes, has added another layer of complexity to our understanding of galactic evolution. Some of these ghostly galaxies may be the remnants of normal galaxies that have been partially disrupted by tidal forces during close encounters with larger galaxies. Others may represent a distinct class of objects that formed in unusual environments or through processes that we don't yet understand. Recent observations have also revealed the existence of galaxies that appear to be completely devoid of dark matter. These objects, which should not exist according to our current understanding of galaxy formation, may be the products of extreme tidal stripping during galactic collisions. If confirmed, these observations would provide crucial insights into the nature of dark matter and its role in galaxy evolution. The study of galactic collisions has profound implications for our understanding of the ultimate fate of the universe. Current cosmological models predict that the expansion of the universe is accelerating, driven by a mysterious force called dark energy. If this acceleration continues, galaxies will eventually be carried apart by the expansion of space faster than they can fall together under gravity. This would mean that galactic collisions will become increasingly rare as the universe ages, eventually ceasing entirely as galaxies become isolated in an ever-expanding cosmos. However, within gravitationally bound structures like galaxy clusters, mergers will continue to occur even as the universe expands. These local regions will continue to evolve through collisions and mergers, eventually forming single, massive elliptical galaxies surrounded by vast halos of dark matter. In the far future, these galaxy-sized objects may be the only remaining structures in a universe that has expanded beyond recognition. The implications of galactic collisions extend far beyond astronomy and cosmology. These cosmic catastrophes raise profound questions about the nature of existence itself. If galaxies, the largest organized structures in the universe, are temporary entities that are constantly being destroyed and reformed through violent collisions, what does this say about the permanence of anything in the cosmos? Our own galaxy, our solar system, our planet, and ultimately our species are all products of processes that began with the collision and merger of smaller structures billions of years ago. The realization that we live in a universe of constant change and violence on the largest scales forces us to confront our own mortality and the transient nature of everything we hold dear. The stars we see in the night sky, the constellations that have guided human navigation and mythology for thousands of years, are all temporary arrangements that will be swept away when our galaxy collides with Andromeda. The very atoms that make up our bodies were forged in the nuclear furnaces of stars that formed during ancient galactic mergers, lived brief but brilliant lives, and died in explosive supernovae that scattered their enriched material across the cosmos. Yet there is also something profoundly hopeful about the story of galactic collisions. These cosmic catastrophes are not just agents of destruction, they are also the universe's primary mechanism for creating new structures and possibilities. Every collision triggers the formation of new stars, new planetary systems, and potentially new opportunities for life to emerge and evolve. The violence of galactic mergers is creative violence, the universe's way of recycling matter and energy to build ever more complex and beautiful structures. As we stand on the threshold of a new era in astronomy, with increasingly powerful telescopes and sophisticated computer simulations revealing the secrets of galactic evolution, we are witnessing the universe's most spectacular dance unfold before our eyes. The collision of galaxies is not just an astronomical phenomenon to be studied and catalogued. It is a fundamental process that shapes the cosmos and determines the conditions under which life can exist. In the end, the dance of galaxies reminds us that we are not separate from the universe but intimately connected to its grandest processes. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created in the hearts of massive stars that formed during ancient galactic collisions. We are literally made of star stuff, the products of cosmic violence that played out over billions of years before our planet even existed. The next time you look up at the night sky, remember that you are witnessing just a single moment in an eternal dance of cosmic giants. The peaceful stars you see are participants in a violent ballet that has been unfolding for billions of years and will continue long after our species has vanished from the Earth. We are privileged to exist during this brief moment in cosmic history when we can observe and begin to understand the magnificent violence that shapes our universe. In doing so, we discover not just the secrets of the cosmos, but something profound about our own place in the grand scheme of existence.